Okay, I think we can start now, Sergita, if you are there.
All right. Good morning, everyone. It is my pleasure to introduce Dr. Matthew Gombolay, who is an assistant professor of interactive computing at the Georgia Institute of Technology, USA. He earned his PhD in autonomous systems from MIT in 2017. His research interest lies in designing robots that can learn from interaction with people and their environment, explain to their human partners what was learned from these interactions, and collaborate in diverse human-robot teams. He has also served as the technical staff at MIT Lincoln Laboratory, transitioning his research to the US Navy and earning an R&D 100 award. His publication record includes a Best Paper Award from the American Institute of Aeronautics and Astronautics and the IEEE Conference on Human-Robot Interaction, as well as finalist awards for the Best Paper in CoRL and ACC. Dr. Gombolay has received the Early Career Award from National Aeronautics and Space Administration and the National Fire Control Symposium, and was selected as a DARPA Riser. And very recently, he has also been awarded the prestigious NSF Career Award. Thank you, Matthew, for accepting our invitation, and over to you.
Thank you very much. It's a pleasure to get to share our research with you that we're doing in the Cognitive Optimization and Relational Robotics Laboratory. I want to focus today on interpretable and interactive reinforcement learning for human-robot teaming that's going to enable humans to specify their values and intent to machines, embodied robotic systems, or virtual agents to help humans with assistive tasks in decision-making and in physical action. Let's start with a motivating example in healthcare. This is the labor and delivery floor where women deliver their babies at Brigham and Women's Hospital in Boston, Massachusetts, where I lived for 7 years. And I got to work with the resource nurses, pictured left here, and she's basically running air traffic control, deciding which patients are going to go to which rooms, of various types of rooms, and which types of nurses and scrub techs are going to take care of them, depending on how their labor goes. She is in charge of 28 direct reports on staffing, looking at various computer terminals. There's displays for the fetal heart rate tracing and contraction pressures for the mother, and then, believe it or not, most of the information on the far right for deciding which patients are going to go to which rooms, and also information about those patients is represented in rows and columns with a dry erase board. And in my work with my PhD advisor while I was still at MIT, and her husband, as Julie Shaw, and then her husband Neil Shaw at Beth Israel, we got to explore whether or not we can have a robot assist these nurses in decision support and controlling or providing decision support for who should do what, when, where, and how. Why won't we do this? Well, hopefully I've motivated that this domain is hard. It's actually worse than air traffic control, unlike an airplane that you can say land on runway 35 right in 2 minutes. You can't just tell a woman to deliver in the way you want exactly at the right time. Emergencies happen, and unfortunately the burnout rate of nurses is tremendous. Half the nurses that I worked with quit serving as the resource nurse in just the 2 years that I was working on the labor and delivery floor. And I'd show up and they'd constantly ask me, Matthew, where is my robot? And so that's what we did. I used an approach based on apprenticeship learning, where we would take expert decision-making from charge nurses, run that through an apprenticeship learning algorithm of learning from demonstration, where we would have descriptions of the state of the world. So that manual dashboard, the dry erase board that I showed you, that describe all the women on the floor, the rooms, their age, their gestational age, the number of babies that they had had before, and other key metrics. And then we would know the various actions that you can take. So who do you put where, and who's going to take care of them through time. That can be changed. And we're going to try to, for those states and actions, we're going to try to learn a robot policy pi hat that is going to minimize the divergence here, the alpha divergence between the human experts policy pi star, given the state of the world, mapping that to the actions that the human would take, and then what the robot's policy would be, pi of s. And depending for this expectation, whether you're drawing your states for your training, your policy pi from the distribution of states induced by the human teacher versus the robot learner, that gets you the difference between behavior cloning and imitation learning. And so we collected our data set of expert nurse decision making, developed a full stack robotic system that would use its own onboard perception to take in information from that dry erase board and be able to use CMU Sphinx and some rudimentary speech recognition and text-to-speech capabilities. Surely it would have been nice if I had GPT-4 Omega back in the day to help me. And we deployed the system on the real labor floor.
Ginger, what's a good decision?
I'm just going to see if I can share sound and
I don't know if you plan to go back and watch it. For me, it was like this the one. We always plan to go back.
Ginger, what's a bad decision?
We don't know.
I agree.
so those were real decisions about real patients. And with only about 2.5 hours of training, wall clock time of training and data collection, we were able to get about 90% of the advice recommended by our robot accepted by experts. And when we had the robot recommend bad advice by picking actions that we thought nurses would not recommend, that also about 90% of the bad advice was rejected, which is a pretty nice result. In this paper that we published in IJR back in 2018. The robot's not there, but it was a very informative milestone that's really set up my laboratory at Georgia Tech and what we're trying to pursue. And I'd like to share with you 3 of the key lessons learned from that deployment of a robotic system in a hospital for how we might improve value alignment and adoption for robotic systems. So first, users want to know why to inform whether they should rely upon the robot and trust it. I thought it'd be pretty cool that the robot would give good advice. That's not good enough in safety critical applications. You need to be able to explain. And then second, for that explanation, or really often it's just a post hoc justification of a proposed action, the robots are going to need to dialogue. They need to interact through natural language, both to receive feedback and critique from the teachers and the people that are in their environment, but also to explain their own behavior. And then lastly, users, whether it be nurses or people like grandma and grandpa in the home with assistive robots, were imperfect, biased, and susceptible to robot influence. For example, in the work that we did in the hospital, we found that nurses' decision-making degrades with increasing workload. We also found that nurses have unwritten rules that they don't necessarily want codified by our algorithms. For example, there would be a reputation of some nurses that are better at taking care of patients than others. And maybe personality traits are a part of that. And unfortunately, that goes into the data. And you may not always want it represented, or maybe we actually don't want biases to be baked into the system just because they're in the data. And so I'm going to talk about these 3 challenges in the work that we've been doing in my lab since I started at Georgia Tech. So first, let's talk about what are we doing to enable robots to explain why the why behind the knowledge that they've acquired. This is a joke that I credit to Bradley Hayes at CU Boulder, and it goes, "Why did the neural network cross the road?" Well, I don't know, but look, it did really well. And that answer is great for a lot of people in computer science, but there's a growing recognition of the importance of explainable AI, and this is very true in safety critical applications. And unfortunately, there's like a common belief that interpretability or explainability of a system, and it's the accuracy that the machine learning model affords you is a direct trade-off. That's zero-sum game, and I think Cynthia Rudin et al. Have been pushing back on this, and I will as well, that I think actually we can have sparse interpretable models that are high performing with some key assumptions, of course, like we have nice features that might afford some kind of linear separability. The first thing that I'm going to contribute today technically is relook at decision trees. Decision trees are a gold standard in interpretable machine learning and healthcare and other safety critical domains. And we're going to think about a simple classification tree. We're going to take in a set of features, run it through decision nodes that are going to look mu, that are going to look at some splitting criterion, look at some feature X with index J. So the jth feature established at node eta, and see whether that feature is greater than or less than some splitting criterion for that node phi sub eta. And if yes or no, we're going to then navigate through the tree down to a leaf that will give us an action that we should take, or a label, or some kind of prediction. And this is not really amenable, though, to reinforcement learning. You can use CART and offline algorithms to train this, but you're not going to be able to update it online through gradient descent, which is a key technique used in modern machine learning and reinforcement learning in particular. But what if instead we used a fuzzy or soft approximation of our splitting criterion, so that here we actually use a sigmoid function where we have feature selector terms beta for each node, and we're going to learn the weight and with some L1 regularization of whether or not each feature should be included in a decision node. And so now we've converted our tree into something that we can train through gradient descent or ascent, and our leaves are going to end up being probability mass functions or probability density functions conditioned on the state of the world. And we're going to learn those probability distributions, and the output of the tree is a joint probability then. How are we going to train these differentiable decision trees with reinforcement learning? Well, Sutton and Bartow and many others have looked at function approximation reinforcement learning and shown that, unfortunately, Q-learning is not always our friend. And so in our paper led by Andrew Silva, who's now at TRI, shown in our AI stats paper that policy gradients work much better than Q-learning, because Q-learning with these differentiable decision trees tends to introduce additional critical points and the optimization curve that tends to cause divergence when training online with gradient descent. Whereas policy gradient curve shown in gray as a function of a splitting threshold for a specific node, that this is the singular parameter we're training on, and this is the optimization service, that policy gradients have a much nicer shape to learn the global optimum for. And so we applied differentiable decision trees on a set of OpenAI gym environments and StarCraft 2 mini battles environments against a neural network, and found that we're able to achieve as good or better performance than the multi-layer perceptron when we're not worried about having to regularize the tree after training to be sparse and Boolean. So this is great, good win that I think, interestingly enough, for these kind of robot control problems, I think the structure of a tree, unlike a fully connected neural network, allows for some kind of thinking about like a bang controller or something programmatic or heuristic for these kind of simple, more, I guess, robotics-like control problems. Now, if we want to get a sparse tree out afterwards, we can apply our L1 regularization and then kind of cherry pick a good model through cross-validation. We are going to take a hit in performance as the model is more sparse, but we're still able to maintain pretty good performance and even outperform the multi-layer perceptron and the state action decision tree. So this baseline against the state action decision tree, I'm actually going to elaborate that more on the next slide. Some people may say, why not just collect a batch of data of deep reinforcement learning with a neural network, for example, on CART poll, collect a bunch of state action pairs with the optimized policy, and then train a decision tree offline in some kind of policy distillation. What we find when you do that, even for simple problems like cart pull, is that the policy you get out may accurately describe under the distribution of states induced by the neural network. It's accurate in predicting what the neural network would do. But when you run it as the decision tree as a policy, it's really bad due to the issue of covariate shift, that you're now in a distribution of states induced by the policy rather than the neural network teacher. And instead, if you optimize the policy directly with our approach, we're able to get much better performance. And so we have both the policy and the explanation as the same thing. And so our work was cited by Ruda and et al. Towards kind of one of the 10 grand challenges of interpretable machine learning for, in this case, reinforcement learning. Since then, we had a publication by Pelagio et al. In 2022 at RSS, where we extended this to continuous control problems, where now the leaves, instead of being a probability mass function over discrete actions, we can now have continuous actions and multivariate continuous, so multidimensional, multiple degrees of freedom continuous actions. And we improved the differentiable mechanism by using the straight through trick and a Gombolay softmax to improve the ability, our ability to get a sparse representation out, applying to a list of standard OpenAI gem and benchmarks. And also we're actively transitioning this with Ford Motor Company for autonomous vehicle control, which has been some pretty exciting work. So we have a nice way to represent what a robot has learned, and maybe humans can inspect that. And we have some work showing that with that, assessing how interpretable decision trees are. Can you use them for tasks like explanatory debugging, where people can follow the logic of a decision tree and predict what a robot is likely to do at the next time step, or why the robot might have made an error. But we actually don't just need that. We need to make this system multimodal and interactive to dialogue, and enable people to actually inject their own values into the system, not just with demonstrations or data. We also want people to be able to use language as a way to augment this, or to specify the reward function that we're synthesizing our decision trees against. So how are we going to do that? First, we're going to look at behavior specification, where we're going to, as part of this is work that's ongoing by Pradyumna Tembwekar in my lab, who will hopefully be defending his PhD this summer, where we did a data collection on Amazon Mechanical Turk, where we took a data set where people would describe the behavior that they wanted in a robotic agent through unstructured natural language. We had a training data set. We also asked them to specify a decision tree with a user interface that we developed. We can then train a differentiable decision tree. We can transfer, so we can learn a mapping from their natural language into the tree representation that they specified, using training data. That can then be directly converted into a differentiable decision tree. And then we can use reinforcement learning. So here, this natural language pipeline is allowing a warm start for a reinforcement learning agent, and also help regularize the agent's behavior to a natural language description of the human's expectations. And so we built a Mechanical Turk interface, example shown here. We have features with splitting criterion listed here on the left, and people can drag their choices for leaves in red and decision nodes in blue into their tree to accompany their natural language descriptions of what they want the robot behavior to be. And we've developed a machine learning framework that uses this data set to convert natural language descriptions into lexical decision trees. The approach, which we called leverage prior work in hierarchical attention networks, and we augmented that to call it Han2Tree, in which we're going to take in words as tokens and pass that through recurrent units, and use various forms of, say, BERT embeddings, or whatever latest flavor of word embedding model that you might want to use. and apply some hierarchical attention, and then pass that through a decoder that then follows a tree structure where you're going to predict tokens for whether you should split or define the properties of either a leaf or decision node, and then whether or not you should split again, and so forth in this recursive program. And we provide some specification for specifically the gator recurrent unit and attention that we're going to be doing at on the word by word level. And then we also added a sentence level attention to kind of help with this document level description of a behavior policy, is that you need to reason hierarchically within a sentence about the specific words, decode parts of each node in our tree, but then we need to reason about the sentence by sentence to get the structure of the tree itself. And so every time a non-terminal node is predicted in our decoding framework, we create 2 new branches of the recurrent neural network, and we recondition. And then new branches are reconditioned hierarchically using special tokens for the left and right branches respectively. And that encoder level attention is reapplied to the parents. So how well does this work if we actually get our trees out of natural language and use that to warm start reinforcement learning? Well, it works pretty well. We found that when we use HARL, our model, to create decision trees, we can translate that into a differentiable decision tree, as I mentioned, and then do PPO, proximal policy optimization, on the initialized decision tree. Now, in a couple of data sets we collected, one for taxi, so that's we asked users to imagine that they have a robot taxi or an Uber that can go to various locations in a city to collect passengers and try to maximize their profits given supply and demand statistics and traffic conditions. And then highway is a standard RL benchmark for navigating a highway as quickly as possible without crashing. When we compare it to neural networks, random initialization, we find that language initialization helps the reinforcement learning agent to start off with a better policy and terminate with a better policy across our benchmarks. Which was an exciting result that we published in Robotics and Automation letters. But behavior specification is useful, and the users in our previous work could actually then inspect the decision tree that's been learned out of the optimization process. So the robot can then say to you, hey, you specified language to me. I can show you the decision tree that I optimized based upon this language specification you gave me. Is that what you want? And maybe that can set up a dialogue. But behavioral specification may be hard in complex domains. Just like it's hard for us to describe what a cat or a dog is in an image, we use deep neural networks to do that. Maybe it's hard for us to specify the how we want robots to accomplish a task, but we can say something about what the termination conditions should look like, what the goals and constraints of a desired robot behavior might be. And so that's what we explore next. And this is kind of envisaged by problem of interpreting commander's intent. So this work's funded by the Office of Naval Research, where commander may need to specify to a decision support tool for planning what the parameters of the mission are, what the rules of engagement are, and then have a automated planner synthesize a plan against the goals and constraints as defined. And this has analogs for sports like team sports, search and rescue tasks, and more. And we set up in the board game Risk, which is a stochastic environment requiring scheduling and resource allocation. It takes hours upon hours to actually play the game. And it's relatively intuitive for most people who we aren't all experts in military planning. So Risk will have to do for us, and we can train our users fairly well in the rules of Risk. And so as before, we collect a data set of unstructured natural language where users describe their values, their goals and constraints through unstructured language of what they want a decision support tool to perform for placing their troops in the initial drafting phase. So users give the text, they give constraints, they give goals on a scale from -100 to 100, and then they can even give us their answer of what ideally they would have, where they would place their troops. And participants were provided an initial map of where some adversaries were placed in order to make their decisions. So given the problem set up for us then is given natural language descriptions as a sequence of word tokens and troop selections, we want to build two different models that are going to translate language into one, goals, and then two, constraints. For goals, we're going to assign a value for each goal, and we bin them. We find that generally people are quite varied in actually providing numerical ratings between -100 and 100, so we binned it to be 0, 1, 2, 3, or 4 in terms of its importance. And then constraints. This is hard because we have to predict an unordered set. So we have to predict, we don't really care about the order of the constraints because they're all a conjunction of them. Then we have to pick for each possible thing that they said, we have to predict what constraint they're talking about and what the constraint values or parameterization of that constraint will be. And so we have as input our set of classification tokens that describe what we're trying to do, the language description from the user, as well as potentially what recommended troop selections users might have that we don't have to put that in. We're going to pass that through word embeddings later and use Roberta transformer blocks, and then output our classification embeddings for goals and constraints. And for goals, the goal classification is an ordinal classification task for our bucket 0, 1, 2, 3, or 4, or 5. And so we actually end up using a combination of regression and classification loss function. And that was a tip that I picked up from Professor Judy Hoffman here at Georgia Tech. And for constraints, we would use we had to come up with something because the ordering in which the constraints are expressed is irrelevant. It's the total set, the order set that we care about in membership in that set. And so we used, by Du et al., we used order agnostic cross entropy for training our classification head for the constraints themselves. So first, participants were shown a tutorial with an annotated example of how to do this commander's intent task. We showed the participant a map setup with ego players' troop placements. Participants were then shown the players' placements along with their strategy description. And then we asked the participants, what do you think the goals and constraints of this person might be? And so basically pitting a human interpreter against a machine learning model interpreting the same natural language descriptions and troop placements, we found that our model had a statistically significant better performance at predicting the actual values in terms of goals and constraints compared to a human rater head to head, which either says that machine learning is amazing and that our human raters weren't very savvy, which is totally possible. But we did try to get the best raters online. And so I tend to favor the interpretation that human interpretation of another person's values through language is actually a really hard task for an individual person to do. And that we need lots of data and potentially even more than just data. We need interaction in order to actually do proper value alignment. We've also just quickly in other work by Silva et al. In my lab looked at how language can help us in multitask learning so we can learn task embeddings through natural language that allow better zero and few shot generalization to novel robot behaviors for multitask manipulation. All right, so the last part of my talk now that we've shown that we can have interpretable frameworks for users to specify robot behavior, and that the robot can then explain through decision trees what it has learned and why it's making decisions it is, and that we can facilitate language-based specification and value alignment. We also want to think critically about whether these systems are going to help support people or actually tear them down because of the biases that are in all of us. I'll give one example in our healthcare study is that actually the robotic form factor, the literal robot that we put on labor and delivery floor, nurses were actually way more scrutinizing over that robotic system. They were better able to detect when we were trying to give them good versus bad advice than when we were using just a simple computer interface. That the computer interface actually tricked them a lot more often when we were switching between good and bad advice. So anthropomorphism of the system is one of the key factors in trust that we need to understand. So I started with this joke, and having developed a lot of work in interpretable reinforcement learning so far, I want to ask, though, will any of this actually improve human-machine teaming? What's the point of XAI if it doesn't actually help people? And so in work by Palacio et al., we looked at human-machine teaming for a Minecraft task, where a human and a robotic agent are going to, are basically an NPC, you're going to build a house in Minecraft, and the robot can explain its behavior through a decision tree and also share what it thinks the human's doing through a decision tree. And we did a couple of studies, first looking at when people watched this system playing out between a human and an NPC, we would freeze the screen over, black it out, and then ask people questions about how well they were able to perceive the environment, comprehend what was happening, and predict and then project into the future what was happening through a situational awareness global assessment technique. And second, when we had people actually play with the robot, we varied the type of explainable AI support that they received as a function of their expertise to see if XAI was actually helping them. What we found first is that situational awareness was improved with decision trees versus no decision trees for comprehension and projection of situational awareness. But while humans did say they wanted full insight into an agent's policies and complete policy explanation empirically improve situational awareness, when they actually teamed with the agent, we seem to have information overload occurring. That using full XAI might be better to build shared mental models offline before the task starts to reconcile differences. And then when you actually execute to prevent information overload, just use partial XAI or limited forms of explanations only at the right time so as not to overload or distract users, and really focus on targeted resolution of differences in mental models. And then we also looked at a study where we compared decision trees, counterfactual reasoning, language-based, feature importance, softmax scores or confidence scores, case-based reasoning or crowdsourced explanations, and no XAI, in supporting users and making correct answers for multiple choice tests. In a scenario, for example, Mark has just started running and is trying to train for a local marathon. The marathon is set to take place in a month, so Mark has been training very hard. Unfortunately, a week before the marathon, Mark suffered an injury. Where was Mark injured? If I were there with you in person, I would ask you to select, do you think it's the elbow, neck, knee, or back? There's probably going to be a few of you for each of them, but I think the majority of you are going to say, if you raise your hands, that it's the knee. And that's the quote unquote correct answer. There's no real correct answer because you can't know for sure. But it's essentially a common sense reasoning task. And let's say that you have a virtual robot to help you with this. The robot says the injury would be in the knee. The robot can explain it. I took Mark's upcoming marathon into consideration to determine the injury would be in the knee. So that's feature importance. And then you can pick the answer you want listening to the robot. And then you can say, do you understand what the robot's reasoning and do you agree with it? We did this on a battery of multiple choice chess with hundreds of users on Mechanical Turk. And we found that subjective explainability was correlated with, so your rating of how explainable each method was, feature importance, decision tree, etc., was related with the measure of like how socially intelligent the agent was, whether or not you trusted the system. And it was also correlated with the number of correct answers you gave. The robot purposely gave wrong answers sometimes. We wanted to know if people explanations would help people tease out whether the robot's advice was accurate. And then trust was also correlated with the number of correct answers people got. So in our analysis overall, a takeaway is that The individual mode of explanation, decision tree, probability scores, et cetera, is not important. It's the users, their demographics, personality traits, and other things that drive how explainable they think that form is. And that explain that subjective appreciation or intelligibility, person-specific intelligibility of the mechanism is what's driving trust and reliance dynamics. And we also found, interestingly, decision trees are my favorite thing, right? Decision trees actually were the most capable at tricking people into agreeing with bad advice. I think this has something to do with maybe the foreignness of decision trees for the average American in this case. But good news for us is that decision trees can be easily converted into other forms of XAI very readily because you have the entire kind of policy specification. But I don't want to do this with lay users. We also want to look at actual experts. And so partnering with my wife, Dr. Grace Gombolay at Emory University School of Medicine, we conducted a similar test based upon the concept was like the board exam for neurology. We would have actual neurologists answer multiple choice questions, receiving various kinds of explanations, decision trees, probability scores, and others. And what did we find? Well, first we found that the test was valid. So the more years of neurology experience you had, the better you did on a test condition without any kind of decision support agent. But worryingly, the perceived explainability of the method that you worked with on the horizontal axis and the vertical axis is showing your performance improvement with XAI, explainable AI, versus non-explainable baseline condition with no XAI. That when you are a novice, you have the least neurology experience. The more explainable the method is, the more it helped you do better on our test, and you did better overall. But with the most neurology experience, particularly those that had 10 or more years, you actually did worse the more explainable the method was. And so I think XAI may be incongruent with naturalistic decision makings and experts who tend to perform something more like black box pattern recognition rather than the more naive or simple-minded learning process of a novice who's following heuristics and decision trees and others as a part of their apprenticeship. And then lastly, we also looked at versus our Mechanical Turk study that neurologists are unique, that neurologists actually liked decision trees, and they really did not like confidence scores or probability scores compared to their lay counterparts. And so this motivates the need to study actual experts in the domain that you're targeting rather than just relying on Mechanical Turk. So in addition to these cognitive biases we have, there's also issues in the data. I mentioned one about certain prejudices we may have, nurses may have about some of their colleagues and not wanting to represent that in the data. But we've seen with GPT-4, Midjourney, many other models that there's bias writ large in numerous ways. And this is something that we've been starting to tackle directly with the work that we're doing that are these models are data driven. And so if humans are specifying their values and goals, what if those values or the information we're giving agents is fundamentally biased? This is something that Sam Altman has talked about in his work at OpenAI, that as a gay man, he's uncomfortable with the idea that GPT-4 may be value aligned in a country that has homosexuality punished by death. So GPT-4 shouldn't help you kill homosexuals, but where do you draw the line, and how do you actually think about this in a paternalistic or a user-centered framework? And that is a very difficult philosophical question that we need to wrestle with. And so some of the work that I've done with Andrew Hunt and William Agnew and others has started looking at the potential harms in using foundation models and internet trained systems for robotics, and how robots can actually be trained on these data to follow commands that are physiognomic, that actually you can say very racist things to these systems, and that they will abide by your prejudice and racism unless you do something to intervene. And we've also worked by Andrew Silva and Prajuma Temboykar have also been looking at explainable AI to help understand where the bias in the data comes from if we're learning from user data, and then also how to then mitigate those biases, and then how to develop the right metrics that we can use to ablate the bias within the data. And I think lastly, the key to all of this is that we're going to need to be holistic and participatory and inclusive in the way that we develop approaches for interactive learning systems. And work that we're doing in my lab, a paper that was just accepted to Robotics Science and Systems with first author Aaron Body. We're actually having focus groups with people and with mild cognitive impairment and their caregivers, their doctors, their nurses, their adult children, their spouses. We do focus groups with them. We invite them into a lab to actually program our robots and work with them so we can best understand the design guidelines and the mechanisms to support robot assistance in the home to help people to age in place. So in my talk today, I've wanted to share with you some lessons that I've learned in deploying real robotic systems and safety critical domains, and that users are going to want to know why our agents are making the decisions they are. That interpretable models can give us insight and perform well, and that language is key to communicating values, and that we've been developing work that enables humans to specify through natural language their values, goals, and constraints to robots. But it's still an ambiguous problem and is going to require dialogue and interactive systems. And then lastly, users are imperfect, biased, and susceptible to robot influence. Not all explanations are equally good, and not always do explanations help people. And so we need human-centric approaches to account for cognitive biases. I'd like to thank the amazing students in my lab as well as my sponsors, and I'll be happy to take a few questions. Thank you.
So guys, we have some time now for questions. In case you have any, please come to the microphone. I'm going to turn on the camera up that direction so Matt, you can see you. Matthew, can you see the microphone?
Yes, I can.
Okay, good. So is there any question in the audience? Well, okay, there is a question now. I have one as well.
Hello. Hi, Dr.
Yes.
Gombolay. Thank you for the great talk. My question is, at least for the natural language portion, I noticed you're using the embeddings from, I believe, Roberta and whatnot. I'm curious what you think about using some of the more foundational models, and I wonder if if you think that's good to use, or even maybe perhaps averse to them, might introduce extra biases or even hallucinations. Just wonder what your take is.
Yeah, thank you for giving me a question to wrestle with. Yeah, it's amazing how much has changed in just a few years. It's quite incredible. We are right now using foundation models, actually achieving some really strong results with prompt engineering for those models. And we've reached a parity and then started outperforming a smaller model trained with Roberta embeddings, and then fully training on our data set. So that's quite incredible because the data set's pretty weird. Like most internet data is not us playing Risk. It's like Reddit forums, right? But like yet in this kind of exquisite domain of commander's intent with Risk, these large models seem in unpublished work, well, we're submitting it for peer review soon, that it seems to be doing pretty well with the right prompt engineering. So that's very impressive. Yeah, there's issues like you mentioned with hallucination, but I think what's nice about some of our approach is that when you force the system to reason in a symbolic manner, and you kind of have a verification system that rejects anything that doesn't comport with the PDDL or other formal planning language you have, you can do a lot. Like Bean Kim back in the day showed like you can have logic-based priors over probabilistic models. That can do a lot to help you kind of address those problems. But yeah, thank you for the question.
Thank you.
Hi, thank you for the presentation. So for the first paper that you talked about, the differentiable decision trees, so in the past few years, we have seen like GFlow nets being applied to causal models and some discrete graphs. I was thinking if you have any comments on if it's possible to combine maybe GFlow nets with these decision trees to maybe get better performance?
Hey, that's a good idea. Email me afterwards. No, it's pretty cool. I think we've been also trying to look at graph neural networks, convolutional graph neural networks as well, and trying to find some connections to differentiable decision trees for learning. I think causal learning, like I'm a fan of Judea Pearl's work. I do think that that's the future if we can figure out how to do it well. So yeah, I think there's promise in that.
Thank you.
Matthew, when you talk about the imperfect users, well, I was wondering, there are many times in which for interactive reinforcement learning, we use simulated users, no? So I was wondering if this imperfection can be somehow modeled to be incorporated in these simulated users in order to train faster, quicker reinforcement learning agents?
Yeah, good question. I think we've wrestled in the human-robot interaction community, we've wrestled with this for a while, that like dogmatically we said, well, you can't simulate people. So like anyone who tries is just like wasting their time. And then that's kind of hard to make progress on algorithms because user studies are so expensive. But I think, especially in the NeurIPS and other communities are kind of coalescing around like the Oz of Wizard. Let's actually simulate people, and not just with heuristics, but like, have these kind of noisy models like the Lou Shepherd rule or other like axiomatic ways of representing it. But it's all still based upon some notion that there is like a known reward function, and that people are just like varyingly bad at accomplishing it. And so I think if we're going to do this, we're going to need something much more like a cognitive architecture or something from human factors that starts thinking about multiple resource theory. And are you channeling things on verbal, auditory, manual, visuospatial tasks? And it's going to get complicated quickly. So it's a good question. I think we need more work in trying to come up with good benchmarks that account for the myriad of ways in which people are squirrely, for lack of a technical term. But I think the right framework, if you're a PhD student out there wondering what do, I think you use kind of good approximations that are accepted by the community. These kind of noisy optimal models of people, but then you actually need to follow it up with your user studies to do it well. And if you're going to directly tackle bias, then you need to conduct user studies to collect data that shows the bias within it, and then develop synthetic models. You can train machine learning models of those data, and then you can develop something on there. It's kind of like an in silico model of a human.
Thank you very much, Matthew. Let's give an applause to Matt for his presentation. Thank you very much, Matt, again.
Yep. Thank you, everyone.
We are going to move now to the next presentation.
Okay, so good morning, everyone. Thank you for being here. And I would like to welcome Professor Dana Kulić. She is the director of Monash Robotics at Monash University, Australia. She's she has been also awarded the ARC Future Fellowship. And Dana develops autonomous systems that can operate in concert with humans using natural and intuitive interaction strategies while learning from user feedback to improve and individualize operation over long-term use. So please, Dana, the floor is yours.
Thanks very much, Pamela, for the kind introduction. I'm not sure, I think I'm sharing my screen, but it's not showing up here, so I don't know. There we go, perfect. Thank you. Okay, so thank you very much to Francisco, Miguel, Pamela, Srijita, and Toman for organizing this workshop and for inviting me to participate. So I'm actually very happy with this last question that was posed to Professor Gombolay, because that's exactly what I want to talk about. So this question of if we're going to be doing reinforcement learning for human-robot interaction, what is the role of simulations and simulated humans? So let's start with some background. So we've already seen in other non-HRI context for reinforcement learning, simulations have been very, very powerful and very, very useful. And I'm showing here 2 examples, which if you have done any work in reinforcement learning should be, I'm not sure why this video is not playing. Maybe because the internet, okay, don't worry, the other videos are not YouTube. So the 2 examples that I'm showing here is the NVIDIA ISAC Sim, which has been used extensively for learning policies for both articulated robots, mobile manipulators, as well as bipeds and quadrupeds. And then the other one I'm showing here is the MIT C-Cell Vista, which offers photorealistic sensor data for simulating autonomous driving. So why have these simulated environments been so attractive and so powerful? So the learning agent can kind of make experiments and modify and improve its policy much more safely and quickly than would be possible in the real world. And then in the simulator, we can easily create variations in the environment conditions and scenarios that might be much more expensive and time-consuming in physical experiments. So we can vary the appearance of the scene, we can vary the dynamic properties like the friction, and what that allows us to do is to kind of create a policy that's robust to those variations. So the key idea is this notion of domain randomization. So we create these variations, environment conditions. So here's an example, an early paper from Tobin et al. at IROS. So here the task is to grasp objects from a tabletop. So we want to train a policy to be robust to variations. So for example, the lighting, the location of the objects, and so on. So in the simulator, we create variations in the object positioning, in the color of the object, the background, the camera view. And then, so during training, the robot is exposed to all these variations. And then at test time, when the robot encounters the physical reality, we hope that this actually physical world is just a sample within the distribution of the scenarios that we have already trained. And then the policy will work well when deployed in the real world. So what are the key ingredients we need to make this work? So what we need is we need an accurate model of the environment. So this, for example, for these grasping tasks, this physics-based simulator. We also need a parametrized model. So we need to know what are the aspects of the environment that are likely to vary at test time. And these are the ones that we're going to randomize in the simulation. And what we want is, ideally, we want this randomization space to be as small as possible, because the higher the number of dimensions, the more data we're going to need to generate and the more expensive this training process is going to be. Okay. So this is now, so far, we've just considered robots that are fully autonomous, that are doing autonomous grasping, autonomous driving. So what happens now if we want to deploy this idea for human-robot interaction? Now we have the humans. So what about we just introduce the human in the simulation, right? So one thing we can do is we can randomize over different humans. We can have humans of different heights. They can wear different colored T-shirts. Just the same as if, there was a box. But the problem is that humans are not just another obstacle in the environment. they are also acting and influencing the environment. So it's not sufficient to just vary their appearance properties or physical properties. We also need to figure out what they're going to do and how they're going to impact the environment, and also what the variability of those things are. Right, so we need these two ingredients. We need the model and we need the parametrization. So now if we think about the model, what are we going to model? Are we going to model the human objectives, or do we want to model directly the human policy? And then when we think about the parametrization, what we want is hopefully this very parsimonious representation of the things that can vary across the human population. Okay, so people have already been, this is exactly what Matthew was talking about a few minutes ago, have been proposing these various user models for simulation. And so one approach is this idea that we think, okay, humans are they have some objective, and they are generally acting optimally with that objective with some noise. And we could even think about maybe the amount of noise is related to the human level of expertise, right? So very expert humans have very little noise, but novices would have a lot of noise. And so this is an idea that we have also been playing with, and actually this work was led by Pamela, who is my colleague at Monash. So if we want to, for example, if we want to learn from human demonstrations, we want to move away from this notion that we can assume that the demonstration is perfect. This is, Matthew was also highlighting this in this talk, is that the demonstrator may be an expert, but they may also be tired or a novice. And so on. And so we want to, when we're learning from human demonstrations, we want to capture this notion that the expertise can vary. And so what we want to do is we want to simultaneously learn the objective while also kind of marginalizing over expertise. So here's a kind of a simple example where we are considering navigation scenario. And so we can generate random environments as well as simulated demonstration trajectories from simulated users who have both different cost functions and different expertise levels. And so the different cost functions could encode like differences in user preferences, so which parts of the environment they want to avoid, and what kind of, do they prefer to go in straight lines or diagonal lines, and so on. And so now, given such demonstrations, we want to be able to extract from each user's set of trajectories both their preference, their intent, as well as their expertise. And so if we're doing this in simulation, we can easily show that actually thinking about this expertise is very important, because actually how well you can estimate the reward really is really dependent on the user's expertise. So if you just assume that everybody's an expert, but in fact the users have a medium or a low expertise level, you're actually going to do very poorly at estimating their true objective. And so we can then also apply this with real human data. So if we have what you can see on your left there is we have a human that is providing a demonstration through an environment via teleoperation. So you can see there is some noise in that demonstration because that user interface is imperfect. And then so now what we can do is we can extract from that demonstration the user's objective and level of expertise, and then we can also generate, well, what would that demonstration look like if the level of expertise was perfect? And so you can see what we do is we kind of remove those small kind of noise that we hypothesize is coming from just the imperfect demonstration. Okay, but here what we're assuming is we're assuming this simple model where we just like people are acting optimally with some some level of noise depending on expertise. However, we know very well from the psychology and behavioral economics literature that this is not a perfect model of human behavior. So oftentimes humans don't act optimally, and often they exhibit these consistent biases. So one very nice idea is we can improve our models by incorporating these well-known biases. So a really nice example is from the work from Kwan and colleagues who incorporate this notion, what's known as cumulative prospect theory, in their human model. So they introduce additional parameters that influence how a person perceives a reward. So for example, if people are more sensitive to a loss than a gain, this might influence how they behave. And this is still a generic model, but just so introducing this notion of optimization with some bias. Now, the other kind of models are models that are task specific. So where we say, I'm not trying to model kind of any arbitrary task, but I'm focusing on a specific task where I'm interested in doing human-robot interaction. So one area that's received quite a lot of attention is modeling pedestrian behavior, right? So let's say I want to have a mobile robot that's going to be moving through a populated environment. So we can think about like a mobile robot in an airport or in a hallway where other people are moving. And what I would like to do is I would like to come up with a policy that, you know, behaves appropriately, you know, and doesn't run into people, but also not just treating people as obstacles, but making, you know, comfortable and human-like. So one common model that has been used that has been used here is this model called optimal reciprocal collision avoidance model, the ORCA model. And the standard approach is you have, so I'll show you some, I'll show you a video, hopefully this will run, is that you have this kind of simulated environment, and in that simulated environment, you have your robot, and you also instantiate a bunch of humans, and these humans are moving according to this ORCA model. So this very nice video here is from Perez Darpino and colleagues, which showcases the iGibson environment, which can be used to implement these simulations. In Perez Darpino's work, they train an RL policy for socially aware navigation using this simulated environment. So now in this simulated environment, you have to kind of have a control policies for how the pedestrians are going to move around. So in their work, what they do is they use this ORCA model. So the ORCA model hypothesizes that the agents pursue a kind of local optimization of their velocity based on the observed positions and velocities of the other surrounding agents. And now in this model, there is kind of this low number of parameters that, you know, specify what is the agent's preferred velocity, kind of the default velocity, how sensitive they are to the other agents, and also how early they can perceive the other agents, right? So how close to the other agents have to be before they start impacting the simulated human's behavior. And so what's commonly done in these, when people are doing these simulations, is all the humans are just, you know, we choose some reasonable value for these parameters of the ORCA model, and all the humans in the environment just operate according to those same parameters. So there's no domain randomization. And so with our PhD student, Nick Asen, we just looked at, okay, well, what happens if you have trained your policy with just this, you know, everybody is using the same model, and then you just kind of change, you change those parameters slightly. So, you know, for example, you know, changing how much the person is willing to give way to others, and so on. And it turns out that if we train a policy assuming that a single set of parameters for the pedestrian model, but then at test time, the pedestrian behaves just differently from that model, the policy performance is significantly degraded. And so what we've been doing is we've been saying, okay, well, let's just apply domain randomization in iGibson. So basically just train over a distribution over those ORCA parameters, and then see if that can improve performance. And so we've been testing this, of course, in simulation. And we see in simulation the performance is improved, but we have also been running user studies where we actually have users, you know, so now we take that policy that has been trained in the simulator and we deploy it in a physical environment with actual users. And we see kind of how the different, you know, policy trained with no domain randomization versus one with domain randomization performs with actual humans. And what we see that both in terms of space compliance, so how much space is, for what portion of the time the robot is sufficiently far away from the person, as well as the minimum distance. When we have domain randomization, we perform better compared to just the baseline not training with domain randomization, which is very nice. So what we can see here is that we are similar to the results that we saw with physical domain randomization. We're seeing this nice transfer to real world experiments, including with real humans. So another task-specific example that I want to share with you is work that we've been doing looking at shared autonomy for drone piloting. So I'll just give you a quick overview of this task. This work was led by my former PhD student, Cal Backman. So the idea here is what we would like to do is we would like to help a human who is piloting a drone. And so let me play this video. Hopefully this will play. What you can see here, so this is kind of the side view, and in the top is the pilot view. So the objective is for the pilot wants to land at some particular spot. And you can see here that this task is actually quite challenging. There's a couple of challenges. One is the depth perception. So it can be hard to perceive exactly whether the drone is positioned over, over the box successfully. And the other is the actual kind of like joystick behavior. So you may know as a novice pilot, you may know exactly where you want the robot to land, but you may not be able to kind of implement the joystick commands to do so. And so what we would like to do here is to implement a shared autonomy framework where we take this potentially imperfect input from the human's joystick commands, and we figure out, well, where do they actually want to land? And then we provide assistance to help them to do so. Okay, so let me give you a system overview. So the idea here is that the drone is perceiving the environment. So it has a camera that's looking down to see kind of like what the environment looks like. And the drone is also receiving as input information from the human flight controller. And so from those two sources, what we want to do is to figure out some kind of policy. So like what should be input as the command to the drone. And what we do is we take the input that's coming from the human user, from the joystick, and the input from this policy module, and that is what goes to the physical drone. And of course, we also measure to help to know where the drone actually is. We use a motion capture system to get the position of the drone in the world. Okay, so now what we would like to do for that policy module up there, we would like to train that purely in simulation. And then deploy this on the physical hardware, so kind of like a pure sim to real, okay? So now the key thing that we need, if we want to train this in simulation, is we need this simulated user model. So here we're using a simulated user model that is not generic, it's specific to this task, right? And we kind of developed this user model based on our experience with just kind of how novice pilots and expert pilots tend to behave. And so the model structure is there's kind of these two stages. One is when the user is flying towards the target, they are in the approach state, and then there is a descent state when they're trying to land, right? So in one case, they're just flying towards the target, and the other one, they're just going vertically down to land. So the user has a perceived goal location that could be more close or farther away from the actual goal location, depending on their kind of perception capability. And so the key model parameters that we have is we kind of, that we want to domain randomize over is this perceptual capability. So how close is the user's perceived goal location to the actual goal? Then we also have a parameter that models the acceptance of assistance. So some people may be very happy to let the assistive system take the lead and they will kind of back off, versus others who want to control themselves and will resist assistance. Then the users may have a different preferred speed, so how fast do they want the drone to fly? And then we also model this variation in joystick operating capability, so how noisy is the joystick input. And so now what we do is we train this assistive policy purely in simulation. And so we domain randomize over the same stuff as all the other regular domain randomization, different lighting conditions, different environments, different locations of potential landing platforms. And then in addition to those kind of environmental variations, We also domain randomize over the pilot input. So we have these 4 different pilot parameters, and we have pilots with different we sample different simulated pilots from this distribution and train a policy. And so our reward function here is we want to penalize any landing error and any velocity at landing. And we also have a kind of regularizing term where we want to minimize the difference between the human and the assistant actions. Okay, so now we have done this training purely in simulation. Now we want to see how well is this going to work when we transfer to the physical tasks. So we ran a user study where we set up these different landing platforms in the lab, and we had participants coming in to basically fly this drone and land it at particular platforms. So what we did during the experiment, you can see there's like numbers at the bottom of the platform. So we would tell the experiment at test time, please try to land the drone at platform number 3. So the participant knew what the target was, but the assistant system did not. So the assistant system had to figure out what was the target just from the inputs that it was seeing from the user's joystick. We had each participant perform this task in 2 conditions, either assisted or unassisted, and the order was random. In each condition, they were tasked with landing on kind of 10 different landings, randomly selected platform. Now note the challenging lighting conditions here. So when we first were setting this up, we realized that if we had the overhead lights on, participants could use the shadow of the drone to help them figure out the depth perception. And we wanted to really make this, to simulate actual challenges with depth perception. So we turned off the overhead lights and we only had these low lights to make sure participants are not getting extra help from the setup. And then we recruited 28 participants, and many of them had 0 drone flying experience, but we also recruited specifically a number from our undergrad UAV club, where there was tons of people who had extensive experience, so that we had pilots of varying piloting ability. And we did not do any training of the assistant beyond what was seen in simulation. So let me show you the results. So here I'm showing the landing error and the success rate. So the landing error is with respect to the center of the platform, and the success rate is whether the robot actually landed on the platform successfully or whether it fell off. So what you can see is the blue dots and the trend line are the unassisted case, and the green dots in the trend line are the assisted case. So in the unassisted case, we see exactly what we expect. The error rate is higher and the success rate is lower for the low proficiency pilots, and then experts are doing much better. But in the assisted case, we basically remove the relationship between pilot proficiency and task performance. So we get every single person performing way better than even the best unassisted experts. And let me show you some fun videos of what this looks like. So here is a novice pilot going to platform 9 unassisted. So you can see this is kind of a typical, so there's like a depth perception challenge as well as some kind of noisiness in the joystick. So you can see this participant's being very careful. They don't want to crash the drone, so they're carefully positioning the drone over the platform. And then, very, very carefully, when they think they've got it, they will slowly try to land. Unfortunately, they're just a little bit off, and the drone doesn't end on the platform and crashes. On the other hand, when we have an assisted novice, you can see that, so from the velocity and the direction, the assistant can already tell that they're going over to the far case, and then once they get above the platform, now the assistance is certain where we're trying to land, and it provides assistance for a kind of strong, highly centered landing. Now, let's take a look at expert pilots. So let me just pause this one and start with the unassisted case. So you can see with experts, we do not help them as much. because they are able to land successfully for the most part without assistance, but we help them with speed and accuracy. So just kind of making it right more quickly to the center of the platform. Now, so this looks very promising, but we did get some feedback from participants is that occasionally they weren't sure what the assistant was doing. They weren't sure if they should, if the assistant was going where they didn't expect what they should do. So what's happening here is that the system is estimating the user intent, but not communicating with the user. And then the other kinds of questions we had is, well, you have purposefully made this task hard on the user. Maybe if you made it a little easier, if you provided some better visual cues, this task would become easier for the user, and they maybe wouldn't even want the assistance. So what we did next is we said, okay, well, can we improve this further by adding visual communications? And here we also wanted to see, can we do this, can we expand the difficulty of the task? So we said, okay, now we're going to have a kind of multi-objective task. So we still want the pilots to approach these landing platforms, but they could do two different things when they approach a landing platform. One task could be that they have to land just like before, but the other task could be that they just need to inspect the target. So they just need to kind of hover over the target so that they can take a good picture. And so for this inspection task, we want, we want the drone to remain overhead, but we want very low velocity so that we could take some, high quality picture. And now we also wanted to compare 3 different kind of visual communication strategies. So one possibility is to just kind of have additional lighting on the drone. And another possibility is to provide a kind of like AR interface where we give some additional visualization to help the user with the task. Okay, so the 2 visual communication strategies that we explored. So one was this AR approach, where you can see here what we show to the user is kind of like where is the location directly below the robot. And so you can see that this is very helpful because I can tell whether the robot is actually above the landing platform or not. And then the other is just kind of this simple, green, so we have green lights, red lights, and so on. Now what we also want to do is we want to learn when, so for this communication strategy of showing the lights, we also want to learn, how to perform this communication strategy. So we apply our same technique of just domain randomization, and now we add this kind of in our model. We add this notion that some participants are responsive to these, green and red light, and they will use green to indicate, good to go to the next task, and they will use red to indicate that we should stop. So maybe I will just, this video is maybe a little bit longer than. Fast forward. So you can see this is basically the domain randomization. So similar as before, but now we have this more complex task, and then we're also modeling this potential partial responsiveness of users to some light communication strategies. Okay, so let's look at the results. So what we see is that regardless of the whether we have communication or not, performance is much better compared to the unassisted case. But we do see that with the lights, so there was no statistically significant difference in performance between no communications and communications, but we did see that participants were slightly faster with the lights and slightly slower with the augmented reality. And we also looking at the subjective responses of the users. There was a very divided opinion on the comms interface. So some people really liked the AR and were just like, oh, this is perfect, this makes it so much easier. But other people hated the AR. And I think maybe it's related to how well the AR goggles fit on the head. And some people complained about making them dizzy and nauseous and so on. So this question of how do we best communicate with pilots, with users during shared control, I think is still very much an open question. So to summarize, we saw from this last example is that, with this kind of domain randomization sim to real, we can actually achieve effective assistance that eliminates the variation in performance between users of different skill levels. So it's kind of like very interesting for applications where normally pilots have to undergo extensive training to be able to operate drones. And if we can use this kind of system, we could eliminate this kind of pilot training. And we've trained the policy entirely in simulation using this parameterized user model. But of course, there's some significant limitations to our approach because this user model is really kind of like very task specific. And to kind of generate a user model like this for another task, you'd have to kind of think carefully, well, what are the kinds of, how does the user typically behave? What are the domains of variability? So I think there's an open questions of how to generate these good but parsimonious models of human behavior for many different tasks. How do we identify, the objectives, so what the person is trying to optimize, and how do we identify these key dimensions of variation that we want to use during training? And then the other thing that we observed during our experiments is that there is also some kind of behavior adaptation during interaction that we didn't model in our system. So we saw, for example, that when people were flying our drone, initially they were very, very careful, but when they saw kind of what the assistant could do, then they started becoming less careful, and some participants even kind of went into testing behavior, so they would purposefully try to crash the drone to see if the assistant could overcome or what it would do. And so then we also saw people's kind of changing, so initially they were flying very carefully and slowly, but when they saw kind of what the assistant could do, they started flying a lot faster. And so, and this is something that we didn't really, model in our simple user model. So I think there's lots of interesting kind of research thinking about how to develop these user models that handle both kind of short-term tasks as well as kind of long-term human adaptation during collaboration. So I would like to thanks to all my students, collaborators, and sponsors, and thank you very much for listening, and I'm happy to answer any questions.
So if you have a question, please come to the mic. And people in Zoom, you can also write your questions on chat and I will read them aloud. Please go ahead.
Yeah, thanks for your awesome talk. I was wondering, maybe I missed the detail, but during the drone-assisted landing, how did it work on a technical level? Like, how did the assistant actually help the user land the drone? Like, was it corrected actions?
Yeah, so if I'll just go back to, I mentioned this briefly, but maybe I didn't highlight it enough. So let me just show you the kind of system overview. There we go. So what we're doing is we're getting, the input from the user is basically inputting the desired velocity of for the drone in Cartesian space, right? And then the policy is also outputting that same thing, and we just average them together.
I see.
And then that is what goes to the low-level flight control.
Okay, thanks for the clarification. Cool.
Then I have a quick follow-up question. So what happens if these actions are very incompatible? Like one wants to go that way and the other one that way, then it cancels out, or?
Yeah, so during the training, one of our cost terms, like for the reinforcement learning, was to minimize this discrepancy, right? So we were actually, so the assistant is kind of trying to help, but also trying to minimize the discrepancy between between the user and its input. And what we saw, so kind of like an emergent behavior of that is when we analyzed when we look over kind of all of the flight trajectories, where the assistant is helping a lot, or, like just the magnitude of the assistance, what we see is that when the drone is kind of flying overhead between, between platforms, the assistant is not helping as much. But if there is like a strong input from the user, then it's kind of that provides more of the signal to estimate the intent. And then the assistant starts assisting more. And then as the person starts approaching a platform, then the assistant's like, okay, now I'm certain you want to go here. Now I can assist even more. And then in terms of the kind of like subjective experience, what you feel as the user is like, if you're kind of piloting the drone, and if it starts kind of going, somewhere where you don't want to go, if you apply a stronger signal, it will stop because it's basically will kind of, now it's sensing that it's not gotten it right.
Okay, so in some way it figures out if what the user is doing is like the same thing it should assist with, and then it contributes and otherwise not.
Exactly,
okay.
Exactly.
Oh, cool, thanks.
Yeah.
Thanks for the presentation, and I wonder that, so will this assistant system like real-time estimate human intention? Because, for example, now in the beginning I tried to landing in the box 1, but maybe in the middle I change my mind, I want to land in the box 3. But I mean, what will happen? Will the system still help me to land in the box 1, or it will change? Because during the training you basically learn from some initial state, but landing in the target specific one, right?
Yeah, so actually the system, so it's kind of only taking, this like current state into account. So the policy is mapping from the current state to action. So if the user starts, generating inputs that looks like it strongly wants to go to 3, then that will also be reflected in the policy. And we do have a little bit of a time history because we are also looking at the previous state. So we do see like so there is a little bit of a delay, right? Between, when you start saying, okay, I really now want to go to 3 to the time that the system reacts. So we do see, like if you so if you're still kind of above the platform, you can successfully shift it from 1 to 3. But if it's already so close to landing that it's almost landed, then, it's kind of too late and the drone is already landed.
Okay.
But so this is kind of, it's not fully satisfying the user intent in that case. But I think what's nice about this platform is like now at least the drone has safely landed. And so then you can lift and try again to go to...
You can restart again from the new, yeah.
Exactly.
Oh, thank you.
Yeah, you're welcome.
Thanks for the great presentation. My question is regarding the one before the drones. Like you have mentioned that the robots, like they don't consider human as just obstacles. They like try to make humans comfortable. So my question is regarding, is that algorithm which you are using there is can it categorize humans as human, like not as obstacle when there is no human movement, if they are just still there?
Right. So let me just go back to that slide, kind of that's showing. So the idea here is that you are in a human environment and you want to generate a policy for kind of this like socially aware navigation, right? So when you're training in the simulator, you know exactly who are all the humans, right? That's you have the underlying ground truth, and you know exactly what their position is, and and how they're moving, right? So in the simulated environment, you can also, in the simulated environment, you can formulate your reward to be, so I have some cost term, some reward term that's related to achieving the goal, so the robot wants to get from A to B, so there's a term for achieving the goal, but I also have some kind of term that I want to keep the person comfortable, so maybe I want to keep a larger distance from the person than I do from the other obstacles, so it's fine maybe to just brush against the wall, but it's not fine to brush against a person, right? And so in the simulator, when I'm training this policy, I know like where the people are, and so even if they're standing still, I know where they are. But you're absolutely right. Now, when I go to deploy this policy on a real robot, so there is the question of, okay, the robot is generating the policy, but there is now also the question of sensing, right? Because that's the other advantage of the simulator, is you kind of remove the problems of sensing because you know perfectly well where everything is in the environment. But now when you want to deploy this on the physical, like on a real experiment, you have to also sense where the people are, right? And so now whether you do this, in a more lab-based experiments, maybe you do this with, motion capture, where you, again, have very accurate positioning of the person, or maybe you try to do it with only onboard sensing on the robot, in which case, yes, you can have these errors if the robot incorrectly perceives that a person is just a piece of furniture.
Yeah. I mean, it's kind of difficult to categorize when a person is still without any movement, whether it's an obstacle or a human.
You're absolutely right. Yeah. So in our experiments, we did have we had people walking around in this kind of hallway environment, but we asked them to either walk slowly, walk quickly, and we also had a case where we asked them to walk while on their mobile phone, which thought that was like a very important test case to include. But we never had them just standing still, and which I think, you're absolutely right. That could be a potential failure case, because if your human perception system is relying on motion cues, you may not perceive that the person is there.
Thank you.
Yeah, you're welcome.
A quick follow-up question on that work actually about the state space. So did you simulate sensors, or did you input the ground truth position of the humans?
So I think that in the training we do inject noise in the perception.
I see.
But we don't perfectly like emulate all of the kind of possible sensor. I think it's just kind of Gaussian noise. Yeah.
Okay. But it would still have to like perceive the obstacles through like LiDAR or.
Yeah, so we do have a second, when we're running this experiment with physical robots, there is like a low-level safety system where if we detect anything in front of the LiDAR that's too close, then we just, stop the system.
Okay, cool. I'm curious because I've also extensively worked with iGips and stuff, so cool. Good work.
Great, thank you.
I have a final question. So how do you think we could extend this idea of simulated humans to contexts where behavior is not goal-driven? It's like an open question.
That's a very good question. So can you give me an example of a behavior that's not goal-driven?
I think it's more like in the social context. Maybe I'm doing something for enjoyment rather than because I want to be more efficient or get to a location. So let's say maybe I want to get to a place. It's my final thing, but I would rather just walk outside because it's really sunny than taking the fastest route through the mall.
Yeah, actually, so I think you can still think about this in a kind of goal-driven context, but maybe you need to relax the assumption that the human's goal is constant, right? And so then, so this is kind of very much related to this question that we had earlier, where okay, now initially the person was trying to reach platform 1, but now they've changed their mind and they want to reach platform 3. So I think what you need to be doing then is kind of maybe kind of randomizing over the possible, multiple possible goals, and then performing, kind of like an online estimate of, what's the current goal of this person? Because I think that's a very good example. We see this when we have robots deployed, brand new robots being deployed in public settings. You have people who are happily, they're on their way to work or they're on their way to something, but then they see the robot and they're like, oh, this is cool. Now forget about where I was going initially. I'm going to try to wave my hands in front of the robot or jump in front of it and see what it does. So I think this notion of, this strong assumption that, humans have a constant goal is, I think, is inaccurate.
Okay. Thank you. Let's thank Dana for her presentation.
Thank you.
And I think it's lunch, right? So see you back at 1:30 for the contributed talks.